Have you ever flushed a toilet or watched water spiral down a drain and just kind of paused for a second? That water, well, it's about to go on one of the most incredible, high-tech, and honestly unsung journeys on the entire planet. So let's dive into this hidden world and follow the water. Because what happens next, wow, it's this amazing mix of engineering, biology, and chemistry that, protects our health and our environment every single day. We're going to pull back the curtain on that entire process from start to finish. So here's our game plan. We'll start with how the plant takes in and measures the raw wastewater. Then we get to the really cool part, the microscopic workhorses that do all the cleaning. After that, we'll see how the clean water gets separated out and then the final disinfection steps. We'll also cover what happens to all the solid leftovers, and finally, the systems that keep this whole incredible operation running. Okay, so it all begins right here at the front door of the plant. Before you can even think about treating the water, you have to know exactly what you're dealing with. It's kind of like a hospital's emergency room. You got to run the right tests to make the right diagnosis. To figure out just how dirty the water is, operators use two really key tests. The first one, biochemical oxygen demand, or BOD, is like a 5-day forecast for the biological work ahead. It's basically measuring the amount of food available for the good bacteria. The second test, chemical oxygen demand, or COD, that's more like a rapid snapshot. It gives you results in just hours by measuring pretty much everything that can be oxidized. And because it measures more stuff, the COD value is always higher. By comparing the two, operators get this really complete picture of the challenges they're facing. And talk about being under pressure. For some of the most critical tests, like for fecal coliform, the clock is seriously ticking. Those samples are only good for 6 hours, tops. This isn't some casual process. It's a flat-out race against time to get the data you need to protect public health. The very first thing that happens is purely physical. A massive bar screen catches all the big stuff, things that never should have been flushed in the first place. But the real genius here is this tiny, sacrificial piece of metal called a shear pin. See, if the screen gets jammed, this little pin is designed to break, shutting everything down before the whole multi-thousand-dollar system tears itself apart. An unsung hero, for sure. All right, now we're entering the heart of the plant. This is where the real magic happens, and it's all thanks to trillions of microorganisms that are working for us 24/7. The operators here are basically microbe farmers, and just like any good farmer, they've got to provide the perfect diet for their flock. And that diet has a super precise recipe. For every 100 parts of food, which we measure as BOD, the microbes need exactly 5 parts nitrogen and 1 part phosphorus to stay healthy and hungry. If that ratio gets thrown off, the whole system can crash. Now, this is one of the most elegant things in the whole plant. It's called the modified Ludzak-Ettinger process, or MLE. It's a really clever biological trick to get rid of nitrogen. So first, the water goes into a tank where there's no oxygen. Then, water that's rich in nitrates gets pumped back into the same zone. The microbes, totally starved for oxygen, do something amazing. They literally breathe the oxygen atoms right off the nitrate molecules, and poof, it releases harmless nitrogen gas into the air. Okay, so the microbes have eaten their fill, and the water is getting much, much cleaner. But now you have a new problem. The water is jam-packed with those very same microbes. So the next step is all about separating that clean liquid from the solid mass of bacteria. So imagine you're an operator, right? You look out at this huge settling tank, the clarifier, and you see this bubbles rising to the surface. Uh-oh, that is a bad sign. So what in the world is going on? Those bubbles, that's nitrogen gas. It's a huge clue that the sludge has been sitting in that tank for way too long. It's starting to do the same thing it did in the anoxic tank, and that gas is making the sludge float instead of settle. The fix is immediate. You've got to crank up the pumping rate of the return-activated sludge, or RAS. You're basically speeding up the conveyor belt, getting that sludge out of there before it can cause a bigger problem. The water is crystal clear now, but that doesn't mean it's safe. Not yet. These final stages are all about taking out any remaining microscopic threats before we can return the water to the environment. Disinfection is this really precise chemical balancing act. Sometimes chlorine gets combined with ammonia to form chloramines, which are like a time-release disinfectant. Operators have to watch out for stuff like nitrites, which are total chlorine hogs. They demand 10 times the dose. And this is crucial. Before the water is released, it absolutely has to be dechlorinated to protect fish and other aquatic life. Some plants even use ozone, which is this super powerful oxidant that disinfects by literally ripping pathogens apart at the molecular level. But what about all that sludge we separated out earlier? We're not done with it. This solid material, which we now call biosolids, has to be stabilized to get rid of odors and destroy any pathogens. A really common way to do this is with anaerobic digestion. That's where different kinds of bacteria break down the solids without any oxygen. You can literally see how healthy the process is just by looking at the gas it produces. A healthy digester makes lots of methane, which burns with a nice, clean blue flame. But if the process gets upset, the CO2 levels shoot up, and the flame turns yellow, a big, bright warning sign for the operators. And when I say the rules for managing these processes are strict, I mean they are razor thin. For a digester, the temperature can't change by more than 1 single degree Fahrenheit in a day, or you'll shock the bacteria. For lime stabilization, another method, you have to hold the pH way up at 12 for 2 full hours to make sure every last pathogen is destroyed. Now, none of this stuff happens on its own. The entire facility is like a living system of pumps, blowers, and sensors. And most importantly, it's run by skilled people who act as its brain and its nervous system. Operators are trained to listen to the plant. If they hear a sound like rocks rattling around inside a pump, well, that's not rocks. That's cavitation. Tiny vapor bubbles are forming and then imploding with incredible force, literally eating the pump away from the inside out. Recognizing that sound is an absolutely critical skill that can prevent a catastrophic failure. Managing a plant like this means you have to know exactly where the load is coming from. And it's not just from our homes. A huge chunk, in this case 40%, can come from industrial facilities. And that can dramatically change the nature of the wastewater and the entire treatment strategy. You know, despite all the amazing automation and technology, the human element is just irreplaceable. When you're rolling out something as vital as a new safety plan, the single most critical factor for success isn't the new tech or the rulebook, it's clear, early, face-to-face communication with the people who actually run the plant day in and day out. So, from the drain to discharge, this whole complex journey often takes just a few hours. It's a rapid, incredibly sophisticated transformation that turns what was a public health hazard into clean water, protecting our communities and the natural world around us. It's this invisible system working silently right under our feet, protecting us around the clock. And it really makes you wonder, what other vital, complex systems that keep our world running do we just completely take for granted every single day?